Okay, so that was a review from what we've talked about. So let's talk about something new. So if you've noticed, all the examples that we've done so far with hypothesis testing have all had a claim that involves ultimately a variable that represents a proportion of success. Success being whatever we keep track of. So in this case, it was a proportion of people in a particular ethnic group, or before it was a proportion of heads that you flip for a coin, or it's a proportion of people who have used a certain website, and so on and so forth. It's just a proportion of successes, or whatever you're keeping track of. But not all claims may have a measurement that represents a proportion of success. So today we're going to talk about a claim that has to do with a population mean instead of a population proportion of success. So let's look at an example of when that might be the case. So let's say that you're traveling, maybe not nowadays, but later when we can travel. So let's say that you're traveling and you notice that in this particular country you're in, you notice that the people that you're interacting on a day-to-day basis, the limited number of people, let's say they happen to be less intelligent than the people that you're used to dealing with in your home country. And so one way that you can quantify that is if you look at the average IQ score for the people you're used to in your home country versus the average IQ score for the people of this new country. So if your claim is that the people in this new country don't seem as smart as the people in your home country, then one way to quantify that is that the average IQ for everybody in this new country is lower than the average IQ for the people in your home country. So let's say that your claim is that the mean IQ and so let's say that this country you're visiting, let's call it country B. The average IQ for this new country is less than the average IQ for your home country. And let's say we happen to know the average IQ for our home country, which happens to be 100. It's less than 100. So again, what we're doing is, based on very limited interaction with people of this new country, we're making a claim for the entire country. We're saying the average IQ for this entire country is less than 100. So again, a claim for a hypothesis test always involves a population. So this claim is a population statement. So in order to make a conclusion about this claim, just like before, we're going to look at an observation. And the observation is, let's say you have a sample of 50 people that you've been interacting with. And let's say for those 50 people in this new country B, you have them take an IQ test. And now you have 50 IQ scores that you punch into your calculator, and your calculator will give you the mean and standard deviation IQ score. So let's say that the mean IQ score in the sample of 50, your calculator tells you is 98. And let's say the standard deviation, your calculator tells you is 14. So from this sample of 50, the question is, what can you conclude about the entire population from which the sample was drawn from? Can you conclude that indeed the average IQ in country B is less than 100? So we're going to use hypothesis testing to make a conclusion about this claim for the population. So the only difference is that this claim has to do with a measurement that represents a mean, as opposed to a measurement that represents a proportion of success for the population. So that's the only difference. So it turns out that the hypothesis test we do will end up having the exact same structure. The only difference is that this step, when we go to look at the underlying distribution, this distribution might have a different shape. Instead of a bell curve with a z-score, it might be, in this case, a t-distribution with a t-score. And ultimately, the name of the game is just to decide whether the observation is in the body or the tail. And it will be the same thing here, to decide whether the observation is in the body or the tail. But to do that, instead of a z-critical, we might be dealing with a t-critical. And instead of a z-test, we might be dealing with a t-test. But either way, any critical statistic is always from a table. So instead of using a z-score table, we might be using a t-score table. And any test statistic will be coming from a formula. So instead of the formula we talked about before, we might be looking at a new formula. But other than that, once we get these two measurements, we just compare them to decide whether the observation is in the body or the tail. And then we reach one of these two conclusions, just like before. So the only difference is how we decide whether the observation is in the body or the tail, and these two numbers that we use to make that conclusion. So the general structure is exactly the same. The only, so when we get to the difference, we'll highlight those. But the general structure is the same. So let's go through hypothesis testing to answer this question.
Null and counterclaim.
Okay, so we have the claim, and then now we're going to find the counterclaim in order to identify HO and H1.
Mean IQ in country is less than 100.
Okay, so there's lots of ways that are logically equivalent for us to phrase the opposite statement or the counterclaim. But the easiest one is to keep everything the same except for the directions of these inequalities. So what's left over from less than? What else?
Be greater than.
Greater than, what else?
Equal to.
Equal to, okay. Greater than or equal to. So then the counterclaim would be, everything else is the same except for, instead of less than, we use greater than or equal to. So this will be, the mean IQ in country B is greater than or equal to 100.
Alright, I feel what you're putting down.
I'm trying to put logically, because I'm thinking if it's gonna be one, it's gonna be the other. That's not the case unless the initial claim says equal to, which means you need to prove that it is not equal to. And everything else, put in as much as you can. So is it, if it is this and that, or is it only this? Is there more specific information to label it down? And if it's broad and general, anything that can fit will fit, that is opposite of the original claim. Okay.
Okay, so once we've identified these two statements, now we convert them into mathematical statements. So these are basically already mathematical statements. But instead of using the words mean IQ, we'll use a symbol for mean IQ. So, for example, for the claim, the mean IQ or any mean value for the population will be given by the symbol for the population mean. So contrast that with what we did before, where we used the symbol P that represented a proportion of success for the population. Now we're using a symbol that represents the mean value for the population. So the mean value or IQ for this population represented by country B is less than 100.
Your counterclaim is gonna be that your mean average at country B is greater than or equal to 100.
Good. So the mean IQ for the counterclaim should be greater than or equal to 100.
Different question, because it has the arrow, but it also has the equal to. Is that a two-tailed or a one-tailed test?
Okay, so let me build up to that question. So first of all, in this step, we're just trying to identify the null hypothesis HO. And we've been saying that the null hypothesis is always, look at the mathematical statement, the one that has the equal sign in it. So of these two, which one contains an equal sign? Only the second one. So this one contains the equal sign. It might contain something else, like the greater than, but it contains the equal sign. So this one will be HO. And the other one will be H1. And the reason why we pick the statement that contains the equal sign for HO is we want to build a model on that equality. So equality means that there's a specific number involved, and we want to build a model around that specific number. So in this case, for HO, we basically just want to pick equality. So even though originally it has something more than equality, has greater than, we want to basically take away everything except for equality. And so HO, the null hypothesis, will just be the mean equals 100. So we're going to strip away everything except for equality and call that the null hypothesis. And so the other statement that remains is H1. So the other statement, H1, is that the mean is less than 100. And so the original question was, well, if we wanted to identify the number of tails, we said before that we always look at H1. So H1 is that the mean is less than 100, and so we said that we just look at the number of inequalities. If you have one inequality, it's a one-tailed test. If you have two inequalities, it's a two-tailed test. So in this case, is there one inequality in H1 or two? There's only one. So this is a one-tailed test. But not only is it a one-tailed test, you can actually specify whether it's a left tail or a right tail. So in this case, because the variable is less than the number, less than is to the left on the number line, so it's a left tail test. You can also think of it as, you go ahead and just draw an arrow there, and that arrow is pointing left, so it's a left tail. Okay, so now that we've identified the null hypothesis and the alternative hypothesis, now we're ready for step 2, and what's step 2?
Assume it's true.
Yeah, same as before, we would assume that it's true, but the assumption now is different from before. The assumption now is that the true mean is equal to 100.
Question.
Yeah.
Significance level or confidence level?
Oh, okay. So let's say that I give you the confidence level here as being 99%.
Thank you.
Mhm. So the second step here is assume that HO is true. True mean really is 100. So now we're going to draw the underlying distribution to visualize that. So the x-axis here, our variable involved, will be the sample mean. So it'll be the mean IQ in a sample of the number we observed, which is 50 people. So remember, we've been saying before that if you're dealing with a variable here that represents a sample mean, and you happen to know sigma, the population standard deviation, then it'll end up being a bell curve by the central limit there. But because sigma is not known here, we only know the sample statistics. We only know the sample standard deviation, the sample mean. We don't know the population standard deviation. So because of that, instead of a bell curve by the central limit theorem, this will look like a t-distribution. So when you have a distribution of sample means when sigma is unknown, and that'll be true, practically speaking, in real life, because usually sigma will not be known. This is a population variable, and you only have access to a sample. So when sigma is unknown, and you're looking at a distribution of sample means, you're gonna have a t-distribution, and we've seen this before in chapter 7 when you did confidence intervals and you were trying to estimate the true population mean when sigma is unknown, and then again, we had a t-distribution. So this is a t-distribution.
And being 50 as our quantity for the sample that we had, degrees of freedom is gonna be 49, still gonna end up being 50 regardless. You get that of 1 minus n, or correction, n minus 1 to give you your degrees of freedom.
Okay, good. So in this step, what we want to do is just visualize that if we were to observe 50 people and the true mean was 100, what would the shape of the distribution look like, and what would be the areas in the body of the tail? That's all we want to do to visualize this step 2 here. So again, the confidence level is given as 99%. That means that the area of the body of the distribution will be 99%, and the tails will add up to give the remainder 1%. So the question is here, how many tails are there? So we talked about this before. So we said it was one tail because we look at H1, there's one inequality. Not only is it one tail, it's left tail because the variable is less than left on the number line. So we have one tail test here. So we can go ahead and draw out our one tail. So again, the body of the distribution needs to add up to the confidence level of 99%. And any tails need to add up to the remainder 1%. So this is the full visualization of the step of assuming the HO is true and the mean is really 100. One thing we could add to it is because we're assuming the true mean is 100, that means in this distribution of sample means, its mean will approach this number that we're assuming, 100. So we're going to assume that this peak is where this assumption of 100 is. So the next step, now we're going to incorporate the actual, so to add to this visualization, let's label where this critical statistic is. Let's label where the left tail actually starts. So this will be the critical statistic, and because we have a t-distribution here, it'll be a critical t-score. So this will be t-critical. Yeah, so we're gonna look at the T-score chart. And we only have one tail here. So the way the T-score chart is laid out is the first column will be degrees of freedom, which will be n minus 1, 15 minus 1 in this case. So go to 49, and then go over to the T-score table. The first row will say area in one tail versus area in two tails. I think the table has the first row as being area in two tails. But regardless, the first two row, one will say area in one tail, one will say area in two tails. And because our distribution only has one tail, you only use the row that says area in one tail for 1%. So go to that column, and then meet 49 degrees of freedom, and then look at what the T-score is for that. So what T-score are you getting?
I'm going with 50 since 49 isn't there, I got 1.676.
Okay, very good. So we're looking for 49, but if it's not there exactly in the chart, pick the closest one should be 50. So we're gonna pick 50. Any questions on using the chart?
I have a question.
Yeah.
For 1%, that would be 0.01, right?
0.01, yep,
And we're looking for in one tail.
in one tail, yep.
So when I'm looking at it, it's 2.403.
Oh, let me see it in the chart.
I agree with her, cause I was going off 10% and 20.
Oh, okay, okay. So let's confirm one tail, 0.01. Yeah, it should be 2.403. Thanks. Again, go to 50 degrees of freedom, that's closest to 49. And then go to area one tail, 1%. Go to that column and then intersect it with 50, and you should be seeing 2.403. So that'll be the critical statistic in this case, the critical T-score. That'll be 2.403. So that's the visualization of what it means to assume the null hypothesis is true and that the true mean really is 100. So this is what the probability distribution looks like with the tails clearly labeled. So let's go to the next step and actually incorporate the observation. So we want to ask, is the observation consistent with this idea that HO is true? So now the observation will be, X bar is 98. So we're going to look at 98 here. And we're basically going to ask, isn't the 98 inside the body of the distribution or the tail? So right now it's kind of a toss-up as to which it could be. So we actually need to, we have the T critical for where the left tail starts. So now let's do the same thing we did before, and for this observation, let's calculate the test statistic, or the T-score in this case, T-test, for this data point. So any test statistic, like a T-test or a Z-test before, will come from a formula. So the T-test, and you'll have this formula in your textbook and formula sheet. So T-test should be X bar minus the mean divided by S over the square root of it. So let's go ahead and calculate that. What's X bar in this case?
98.
Yeah. That's given in your sample is 98, and again, X bar represents the mean in the sample. And then minus, this mu is the mean for the population. So again, we don't know that. We don't know what the mean IQ for the whole population of this country is. But there's a step in hypothesis testing where we're assuming that HO is true, so we're assuming that the true mean is 100. So we're gonna use 100 here. And then we're gonna divide by S, which is the sample standard deviation, 14, divided by the square root of n, so that'll be the square root of 50. This is a little bit tricky to enter in your calculator. Make sure you're dividing by this entire quantity on the bottom.
That's curious. I got -5 multiplied by the square root of 2 over 7.
-2 divided, what's that?
So I have a fraction with the numerator being -5 directly by the square root of 2.
Oh, okay.
Overall.
So your calculator is giving you the exact answer, and so if you want a decimal approximation, you can, there's this button.
Right there, 1 second, so I got -1.01.
Yep. That's it. Rest of you guys got that?
Yes.
Okay, great. Okay, so that's the test statistic, or t-test in this case, for the observation. So you can go ahead and label that. So if we know that t critical, also by the way, so your chart gives you t critical for a one-tailed test, but you notice that it's a positive number. That means that when you look up the table and you're looking at one tail, the table is assuming that that one tail is on the right side. But we know that our tail is on the left side, so whatever value we're getting, we're gonna make it negative. So this t critical will be negative 2.403. So if our observation has a test statistic that is negative 1.01, is it to the right or left of that negative 2.4?
To the right.
It's to the right. It's less negative. Good. So it's to the right. So that means that t-test will be negative 1.01. So from this point on, everything will be the same as all the hypothesis test examples we talked about in the past. So now that we got these two numbers we can compare, is the observation in the body or the tail? It's in the body of the distribution. Very good. So because of that, now we go to answer question 3. Is the observation consistent with the idea that HO is true? Because it's in the body, then yes, it is consistent. And if it is consistent, then what conclusion can we make with HO?
Those are
Yeah, fail to reject, very good. So we have one observation that is consistent with this idea, then that doesn't mean that we can accept the idea for all cases. So the best we can do is not throw out the idea. So fail to reject the idea. In this case, the idea under consideration is HO. So fail to reject HO. And if we fail to reject HO, what can we say about H1?
Fail to accept.
Fail to accept, good. So fail to reject HO, fail to accept H1, and we always want to bring it back to the original claim. So the claim in this case is which statement, H1 or HO? It's H1, based on how we labeled it in step 1. So because the claim is H1, we go back and look at what we said regarding H1, which is fail to accept H1, so therefore we're going to fail to accept the claim. And again, just as a review, and one thing I want to emphasize is when we say fail to accept the claim, it doesn't mean that we're forbidden from ever accepting the claim. It doesn't mean in the future we can never accept a claim. It just means for now, based on this one sample, don't yet accept the claim. So on your homework, you'll see there's not enough evidence to accept the claim. Any questions? Okay, and another thing I want to review and emphasize is that fail to accept doesn't mean reject, but you can think of it as leaning towards rejecting. So you can think of this as you're leaning towards rejecting the claim. Any questions? So what does that mean? That means that if you're in this new country where you're only observing 50 people, and the average IQ of those 50 people is indeed a little bit less than what you would expect from your home country of 100, this difference between 98 and 100 is so close that that could be attributed to random chance, and it's not an actual difference. And so you can't just conclude that the average IQ in the whole country is actually less than your home country of 100 just because you're observing this one sample. So the best you can conclude is that you're gonna lean towards rejecting this claim that there's an actual difference. Okay, any questions, guys? All right, so today what we did was we did this new concept of a hypothesis test with a claim that involved this new measure. It was a population mean as opposed to a population proportion of success. And the only difference is this step where we go to decide whether the observation given by a test statistic is in the body or the tail of the distribution. So the only difference is when we go to calculate the test statistic, that'll come from a new formula. And when we go to find the critical statistic, that will also come from a table. But in this case, it'll be the t-table as opposed to the z-score table. And the underlying distribution will be a t-distribution as opposed to a bell curve, like in the previous case when we were looking at a proportion of success. But once we get these two numbers, the two t-scores, then we can decide whether the observation is in the body or the tail. And once we determine that, then everything else is the same as before. Okay, so one other thing I wanted to mention. In the homework, remember we said that you can reach this conclusion about whether the observation is in the body or the tail by comparing these two measurements. The other way that we could have done it, just like before, is to use the p-value and compare that to alpha. So remember, the p-value is you're going to look at your test statistic, and relative to your test statistic, you want to find the area in the same direction as the nearest tail. So that was step one of finding the p-value. So relative to this test statistic, find the area in the same direction as the nearest tail. In this case, the total left area. So basically, you want to look up a t-test of -1.01 or as close to that as possible, and find the total area to the left of that under the T-score chart. The problem with that is that the areas in the T-score chart are very, spaced very far apart. There's only the very common areas. Like if you look in the T-score chart, there's area in one tail, for example, and only the common areas are listed. Only like 1%, 5%, 10%, and maybe a couple more. But only the very common areas. You don't have fine granularity in these areas. So you're not going to be able to find a precise area for this area to the left of this particular t-test. So in terms of p-value, you're not going to be expected to use the table, the t-score table, in order to find the p-value. Unlike for the case of the z-scores, where there's very fine spacing between the areas for the z-score table. So in this case, for the t-score table, you're not going to ask to find the p-value using the table. That said, on the homework, they might ask you to use a calculator instead of a table to find the p-value. And that's just for extra enrichment. So the way that you use the calculator, you're not expected to have a fancy TI-83. You're not expected to have a fancy calculator. But if the homework asks you to use technology, all you have to do is Google the particular calculator you want. So in this case, since you know you're dealing with a t-distribution, you're going to Google t-score calculator. And once the t-score calculator comes up, just pick any of the links that Google suggests. So once the t-score calculator comes up, you're going to use that calculator the same way you would use a table. But the online calculator will give you the precise answer as opposed to using a table. So using the table, recall, you're going to be asked for degrees of freedom, and the table in the book will give you area in one tail or area in two tails. Basically, the online calculator will be the same thing. It'll prompt you for the same things. It'll prompt you for degrees of freedom, which in this case will be, it'll always be n-1. And then once you enter in the degrees of freedom on the online calculator, it'll give you area in one tail and area in two tails. And in this case, if you want an area to the left, you would use area in one tail, and then you would use that exact number your calculator gives you, and then just proceed from there. So to calculate the p-value, you would take that area, and if it's a one-tailed test, you multiply by 1. If it's a two-tailed test, you multiply by 2. But basically, if your homework asks you to use technology, you're not expected to have a fancy calculator. Just Google the particular calculator based on the distribution you're using. Okay, any questions? All right, see you guys next time. Have a good day.
When we take the exam coming up, I'm fairly certain you're not gonna say, Google the calculator and do stuff.
Yeah, so on exams, there will not be use technology questions.
I've run into the use technology a couple of times, and I still try to figure it out manually so I can put it in. And is there a big difference in most of what's going on there? Most of the time you can figure it out manually without a lot of it.
Yeah.
You don't get that much of a change in the answer.
Right.
And I'm not trying to use a calculator to figure that stuff out either.
Yeah, no, we don't expect you to do it.
I wasn't trying to be a jerk by picking that particular question,
No, that was a great question.
it was really frustrating trying to figure out X. Like the rest of it popped up really easy, but it took a while to figure that part, and I was like, And then I saw where I made the mistake here, because that was kind of what I did in the opposite at home, trying to work that problem, because you were looking for the mean, not X. I was stuck on X. It's like, how did you find X? And then that's how you walk through it. And then it was the question about the equality of the, at the beginning. It was like, the computer didn't agree with you, and I'm just trying to figure out why. And the way you circled the word in is like, okay, now we're tracking with what they said and why. I was just trying to figure out why you were saying both instead of one.
No, that was a great question to do together and to point out, all the subtlety that can be involved. I just hope I didn't confuse the class.
I really don't think you did. I mean, they're gonna see that question and
Yeah.
something very, very similar to it if they, miss it the first time or the second, because that's how it's worded. And just like,
Yep.
I know if this is kicking my ass, they probably need like, a move in the right direction. Hopefully you have better words than I do sometimes, so, all perspectives, I'm trying to be helpful, not hindering.
No, you definitely are. Don't worry about it.
And if you need me to shut up in here, I will, I promise.
Not at all, you're good. I appreciate the engagement and participation.
I'm not trying to be your difficult.
I know. No, I appreciate it.
Normally when you say that, it's like, yeah, you're not the problem. Like, if I am, please let me know so I can back off.
No, you're definitely good. Don't worry about it. Have a good one.
Take it easy, boss.
Yep.